Hi, welcome back. In this video, we're going to talk about maximums and minimums. Guess I'm missing an S here, right? When we're identifying a polynomial, such as this, right, there are critical values in the polynomial. Like right here, there is a peak on the polynomial, and then there's a dip on that polynomial, right? Our goal, every time that it changes directions, our goal in this video is to talk about the description, right? What happens at those locations? What do we reach? Are we reaching a maximum value or are we reaching a minimum value? Right? So as you can see here, because it's going up, this part right here is a peak. We call this a maximum value. And whenever it dips to the bottom, we call it a minimum value. Now there's different kinds of maximums and minimums that I want to go for, and then show you a few examples about how to go for it with a graph. So let's talk about this a little bit more. Let me give you another scenario here. Let's say we have something like this. Alright, so we're going to be paying attention to the parts where the graph changes. So something like this, something like this, and something like this. Everywhere that it changes, we call those critical values, right? A peak, or the top of a mountain, we're going to refer to it as a maximum. And wherever the function dips in the bottom, right, we're going to call this point a minimum. Peaks and valleys, if you will. Right? If it goes to the top, it's going to be a maximum. If it goes to the bottom, it's a minimum. So because this is at the top, we're going to call this a maximum. Because this one drops to the bottom, it's going to be called a minimum. Because this one peaks at the top, it's also a maximum. And then that's it. Now notice how here we have two maximums, and one of them is higher than the other one. Because this point is not the highest point on the graph, we call it a local maximum. Because relative to the points around this area, right, if I cover this part of the problem, if you compare this point to all of these, it is a high point. But it's not the highest point, because there's even points that are higher, right? We call this a local maximum, or we even use the word relative. Relative maximum or local maximum. And this one, because it's the highest points of the entire graph, we call this an absolute maximum. Now this point, it's a minimum point. But notice how there are points that go even lower because of the arrows. This implies that it's going to keep going to negative infinity, right? Which means there's no way this point can be the absolute lowest. So we call it a local minimum. Yeah? So we use local, minimum, and maximum when it's a maximum or a minimum on the graph. But we use the word absolute, maximum and minimum, when it is the highest or lowest of all the points on the graph. Like here, right? There's no point higher above it, so we call it the absolute maximum point. And we'll do several examples so that you can see the difference between these, right? But our goal is going to be to identify these locations and to classify them as a maximum or a minimum. And if it's the highest point, we'll call it the absolute maximum. If it's the lowest point on the graph, we'll call it an absolute minimum. So let's try some examples. This is a great opportunity for you to like the video if you're watching. And subscribe, of course, if you haven't. Alright, that was the last bell. Let's get through this. So here we have this polynomial, right? When we're graphing these, to get an idea of where the maximums and minimums occur, we need to first find the x-intercepts. And that happens when you set each factor equal to 0. That turns this into x equals -3 and x equals +2. So I know it's going to cross the x-axis at -3 and at +2. And because this is a positive coefficient, we're dealing with 2, 3, this is a positive x to the third power polynomial. And if you watch the previous video, right, when we're identifying end behavior, we know that the function will look something like this. So the end point over here is going to be pointing down, and on the other side it's going to be pointing up. Now let's identify what happens at each point. As I'm connecting this point and I get to -3, because there's only one value, it's going to go through. And as I go to the next point, because there's two of these, x squared, it's going to bounce back up. Yeah. Now, the critical values will happen, as you can see, here in the middle, at -0.5, we have this point. And then at x equals 2, we have another point of interest, right? We have 2 points that are interesting to us. Now we're going to classify them. Because this point is reaching a peak, we're going to call this a maximum. Is that the highest point in the graph, though? No, it's not, because this graph keeps going even higher. So we're going to call this a local maximum. Yeah, this is a local maximum. And then it dips down to the bottom. Here we have a bit of a dip or a valley. We're going to call this a minimum. Is it the lowest point of the graph? No, because there's even lower points down at -infinity. So we're going to call this one a local minimum. We're not always going to have absolute maximums or absolute minimums, right? It depends on the other points in the graph. Are there higher points or are there no higher points? That kind of stuff. So we want to start by being able to graph it. If you can graph it, then you're going to be able to identify where does the peak happen. And I'll tell you those locations, right? That's basically the middle. At that point, what's going to happen? Maximum. And then at the point where it dips, there's a minimum. Let's try another example. Here we have 3 x-intercepts. If I set them all equal to 0, I get x equals 1. I get x equals 3. And then I get x equals 5. Yeah. And then as I look at this, because this I have 2 x's here, 3 and 4, this is a x to the 4th function. And because there's a positive coefficient, there's no negatives in front of it, it's a positive x to the 4th, meaning that the graph will look like a W of some sort. Some kind of W. So the end behavior will point up and point up. And in the middle, we're going to have all the bouncing and wiggles and stuff. So let's get through this. When we get to 1, there's only one term, which means I'm going to go through that point. And then I'm going to go back to 3, the next x-intercept, and this one's going to bounce because there's 2 of them. Meaning when it touches, it's going to go back down. And then I'm going to go over here, and when I get to 5, I went a little bit behind it, it's going to go through because there's only one term. We have 1, 1, and 2. Now from this graph, we can see that this point right here in the middle, if I cover everything around it, this point there, it makes a bit of a peak, which makes it a maximum value. So I know that at x equals 3, we have a local maximum. Because notice how this point is a high point, right? It is a maximum point, but there's points that go even higher than that. So we're going to call this a local maximum. What about these points? Here and here. What about those? How do we know if which one's lower? How do I know if the graph is supposed to look like this? Or maybe like this? Or maybe like the picture, I drew them the same height. How do we know that? Well, at x equals 2 and at x equals 4, because they both cross the x-axis, they both go below, I need to determine using this function which one is actually lower and which one is actually higher. So let's plug in 2 into the equation, right? I'm going to plug 2 into every x value that you see here. 2 minus 1 2 minus 3 squared and 2 minus 5. I'm plugging 2 in for every x as my input. And then the output of the function will tell me how low to graph it on the graph. So what do we get here? 2 minus 1 is 1. 2 minus 3 is negative 1. I square that, and then I have 2 minus 5 is negative 3. If I do a little bit of PEMDAS, right, I do the parentheses first, and then I do the exponents. Negative 1 squared is 1. So this turns into, I'm going to move it over here, 1 times positive 1 times negative 3, which makes it all negative 3. So technically, I should have drawn this lower. It was earlier it was just a sketch. I couldn't tell how low to go. But now I can determine that it goes to negative 3. Now let's find out if that point goes the same height or even lower, right? That way we can determine which point is lower. So let's plug in 4, because that is the point that's in the middle of 3 and 5. 4 minus 1 times 4 minus 3 times 4 minus 5. And we repeat PEMDAS. Inside the parentheses, we get 3 times 1 squared times negative 1. The exponent gives me 3 times 1 times negative 1, which also gives me negative 3, which means this point in my graph, they're both going to go to the same level. Meaning that since they're both minimums, and they're both the lowest points on the graph, they're both going to be absolute minimums. Because notice how the arrows don't go this way, so there's no points lower, making them both absolute minimum and absolute minimum. It wasn't either of these scenarios. It was where they're the same level. If one of them was lower, let's say that this one went lower, this one would have been an absolute minimum, and this one would have been a local minimum, right? But because they're both the lowest points, they're both absolute minimums. All right, let's try one more. Let's just kind of put all of this together. Last example. All right, what are we working with? 3 x-intercepts. So x equals negative 3, x equals negative 1, and x equals positive 5. Negative 3, negative 1, positive 5. I do have a negative here, which makes this a negative 2, 3, 4, 5 x's. X to the 5th, right? A total of 5 x's there, and it's a negative, which means my graph will look something like this. If you're not comfortable with that, right, you can always go back to my other videos where I show you how to graph polynomials or graph the end behavior of the polynomials. This helps me figure out the graph starts this way and ends this way. And I just got to fill in the gaps in a minute, right? Let's figure out what happens at each point. At negative 3, there's 2 terms. It's an even multiplicity, which means it's going to bounce. Then I go to the next point. Negative 1, there's only 1 term, which means it's going to go through. And then when I get to the next point, when I get to 5, because there's 2 of them, I'm going to bounce back down. Here's my sketch. A roughly sketch. So I have 3 key values that I want to pay attention to. This point, I want to pay attention to what happens here, and I want to pay attention to what happens here at this point. I'm just looking for the middle, right, where the lowest value is, right? I'm going to find the peaks and valleys. I'm trying to identify all of these values in the graph so I can determine what are they, right? So what happens here? At negative 3, we reach a low point in the graph, right? Relative to the points around it, it's a low point. It's a minimum. Is it the lowest point in the graph? No, because there's other points that are even lower. So it's a local minimum. The local minimum value. Then what happens at negative 2? At negative 2, I reach a maximum value. But is it the highest point in the graph? No, there's even points that are even higher. So we call this a local maximum. And then it drips down to this point. At x equals 2, what happens? We have another minimum. But is it the lowest point in the graph? It's definitely lower than this one. But there's even more that go to negative infinity, right? And that point will never surpass negative infinity, which makes this a local minimum. And then finally, when we get to the top, this is the top part of the little hill, a peak, making it a maximum. And then my only question is it the highest point in the graph? No, because there's even higher points in the graph. So this is at x equals 5, it's a local maximum. Notice how we have no absolute maximums here. No absolute max or min. Because this is an odd function. When you have an odd exponent, the arrows are going to point in opposite directions. They're going to go from infinity to negative infinity. So there's not going to be the highest point or the lowest point in the graph. So you're not going to get absolute maximums and minimums whenever you're dealing with an odd exponent. What about even exponents? Right? Like x to the 4th. Since both arrows are pointing up, you will have either this point or this point be the absolute minimum. Or maybe it's like x to the 6, like a negative x to the 6, where it's pointing the other way. When both arrows point in the same direction, one of the sides of the graph will have an absolute maximum or an absolute minimum, depending if it's on the bottom or at the top. We just have to determine which of the points is the highest or which one is the lowest. And for that, we sometimes have to plug in numbers into the equation to determine the difference, right? But for odd exponents, no absolute maximums or minimums. For even exponents, you will have at least one of each. All right, guys, I hope this has helped. Please let me know if you have any questions. Don't forget to like and subscribe. And as always, I'll calculate.